rounded fragments more than 2 millimeters in diameter. When gravels are liquefied and consolidated by cementation, the rock is known as conglomerate. Breccia is another type of similar to conglomerate rocks, but their gravels are sharp-edged rather than the rounded gravels as well as known in the conglomerates. The second type is sands. Sands are composed of grains ranging in size from 2 millimeters to 62 microns. In diameter, most of these grains is quartz, and the liquefied rocks are known as sandstone. From these sand deposits are the sand dunes in deserts. My dear students, the third type of the detritus sedimentary rocks is mud. It is a sediment composed of a mixture of silt, which is 62 to 4 microns, and also the clay, which is less than 4 microns. Both are usually mixed together to form mud deposits as less than 4 microns. Both are usually mixed together to form mud deposits as in the case of the Egyptian soil, which is the Nile alluvium soil. Laminated mud, when mud becomes consolidated, it is known as mudstone. Usually acquires lamination and facility as a result of its compacting, and then it is known as shale or laminated mud. My dear students, let's go to this type of sedimentary rock, which is chemical sedimentary rocks. What do we mean by chemical sedimentary rocks? Chemical sedimentary rocks are formed by precipitation of dissolved load of soluble salts in water. This precipitation is due to evaporation of water and the increase of salts concentration. The most famous chemical deposits are gypsum, hydrous calcium sulfate, and the table salt, which is rich in sodium chloride. These shale deposits crystallize from inland lakes and coastal lakes and sabkhas. Man made use of this phenomenon and extracted table salt from seawater by water evaporation in artificial reservoirs, salinas. There are other kinds of chemical deposits, as some iron ore deposits, with its most famous example. As you see, in Egypt we have the oolitic iron ores, which is made of hematite. It means the red iron oxide, and were deposited at Aswan. My dear students, let's go to the other type of sedimentary rock, biogenic and biochemical sedimentary rocks. What do we mean by biogenic and biochemical sedimentary rocks? We all know that sea living organisms build their inner skeleton or outer hard parts. In this time we call it shells. They build it from calcium carbonate, which they extracted from the seawater. When they die, the hard parts accumulate on the bottom of the sea to form fossiliferous limestone of biogenic origin. Fossils are the solid remains of the sea-living organisms, may belong to vertebrates, as fish and other organisms, or belong to invertebrates as shells, coral reef, foraminifera, and calcareous algae. Also, phosphate rocks contain fossils, phosphate in addition to secreted phosphates minerals of biochemical origin. Also, coal is another kind of economical biogenic rocks. It is formed when plants are buried for a long time inside in the bottom of the earth, away from the oxygen, so the plant's tissues lost their volatile constituents, and carbon gets concentrated, forming coal. This usually happens in swamp areas and deltaic environment of a river, where rapid burial of the plants remains in these reducing environments away from the air. Also, oil and gas, they are not considered as deposits, have been formed and are contained within the sedimentary rocks. So the sedimentary rock here is hosting the economic liquids and gases of oil and gas. Now let's talk about the energy resources in the sedimentary rocks. We have different sedimentary sources in the sedimentary rocks, like oil and gas. Oil and gas are hydrocarbons. It means both are composed of hydrogen and carbon, which have been formed by the decay of microscopic organisms that belong to both the animal and plant kingdoms. These organisms are deposited to be buried with the fine-grained mudstone or muddy sediments away from the atmospheric oxygen. And also when they are buried to a depth of 2 to 4 kilometers, where the temperature ranges between 70 and 100 degrees centigrade, the sediments becomes cooked and the tissue of the organisms decompose to give oil and gas on maturity. The fine-grained mud rich in organic remains is known as the source rock. Oil and gas are usually expelled from the source rock under pressure and migrate to the porous and permeable reservoir rocks, mainly the sandstones and fractured limestone, from which they are extracted. We have another source of energy. We find it in the sedimentary rock. It is the oil shale. Other sediment of economic importance is the oil shale, which is a muddy sediment rich in organic remains, mostly of algal origin. The organic material has a waxy nature and is known as kerosene, which decomposes on heating to give oil. So oil shale yield oil when it is heated to about 480 degrees centigrade. It is an important source of energy, but oil is not extracted from oil shale commercially at present, for the simple reason that cost of the production is still higher than the price of the natural oil. Oil shale is kept as reserves till natural oil and gas deposits have been consumed. And we see nowadays in different countries they start extracting oil from this kerosene. When the price of natural oil has become higher than the cost production of oil from oil shale. Now, my dear students, let's go to the next type here of the rocks, the metamorphic rocks. Metamorphic rocks, they are manifested changes in mineral and texture of the rocks while in the solid state in response to increasing temperature and pressure in the Earth's interior. As you see, my dear students, metamorphism is manifested changes in mineralogy and texture of rocks while in the solid state in response to increased temperature and pressure in the Earth's interior. Accordingly, a metamorphic rock is a rock whose original mineralogy, texture, or composition has been changed by the effect of temperature and pressure. The original rock, whether igneous, sedimentary, metamorphic, when subjected to increased temperature or pressure and temperature together, will respond to become in equilibrium with the new physical conditions. The crystals usually increase in size and are arranged so as to become oriented in directions or least pressure direction. Metamorphism commonly accompanied mountain building movements where temperature and pressure are high. My dear students, we have another type of metamorphism. It is well known, as you'll see. It is the contact metamorphism. As you see, my dear students, sometimes we have massive metamorphism where the increase in temperature is usually reflecting into an aggrading in the process of crystallization, resulting in the increase of crystals. The best examples is the metamorphism of limestone into marble. The original crystals of calcite of similar size of the limestone have become recrystallized to large interlocking crystals of calcite, which we call it marble. This results in greater compaction and lissification. It means hardening, and the rock becomes harder of marble compared to the original limestone. Also, impurities in limestone may also recrystallize or from new minerals of attractive colors. We have another example here, which is the changing of the sandstone into quartzite, also by increasing and the increase of crystallization. Now, my dear students, the second type of metamorphism, it is foliated metamorphism. In this case, the rock is subjected to increase of temperature and pressure. The constituent crystals will be arranged and oriented in a certain direction, and the rock is termed schist or gneiss. This is quite obvious in metamorphism of rocks rich minerals with a preferred oriented direction as mica. A mica schist is a rock that shows foliation due to the parallel arrangement of mica crystals in one direction. This is usually the direction of least pressure, which is perpendicular to the direction of the outside pressure. Now, my dear students, let's go to another subject in our today's program, which is the environment and the balance between geologic activities. We will talk about the drifting of continents and mountain chains. Let's first start with the relation and the balance between geologic activities. Through the geologic time, ecologic conditions varied greatly due to the topographic relief, as well as variations between water-covered areas and land, resulting from uplifting and subsidence of the Earth's crust. As an example of the ecologic adaptation during Carboniferous period, 300 million years ago, was the flourishing of the vegetative cover under warm, humid, and organic-rich conditions. These result in accumulation of huge trees buried deep enough and gave rise to cool seams of various quantities. Also in Jurassic sediments of Al-Maghara are in northern Sinai, also in Central Europe, white rock salt, which is the sodium chloride, and others were deposited during the Permian period, 250 million years ago. These deposits resulted from the evaporation of seawater, filtering and filling large basins, intermittently connected with the open sea under arid climatic conditions. The accumulation also of vertebrates, fish remains, is reported in North Africa during the Upper Cretaceous period, 90 million years ago. As you see, my dear students, we're talking about specific environments in the past, lifted and laid down specific deposits as cool seams, and now we're talking about phosphates and also even the rock salt. All of these are specific environments with intensive sedimentation. So at the time being, this environment is not found anymore. So we have changes in environments. These are the phosphate deposits, as we said, reflecting shallow marine condition of normal salinity and ordinary temperature. Such deposits are of economic value and occur in Egypt in Safaga and Qusayr Stretch, in the Red Sea coast. Also we find it in Sabaya, in Nile Valley area in Upper Egypt, and also in Abu Tarsur, New Valley, Western Desert. Among the familiar variations in ecologic conditions are those recorded during the 1 million years ago. We have a big changes in environment and represented by the ice sheet covering the northern hemisphere, which coincide with the rainy seasons in the southern region of the hemisphere. By retreat of these ice sheets northward, At this time we call it interglacial periods. The southern regions were described as dry areas, interglacial periods. Such climatic variations result in fluctuations of the sea level and the density of the vegetative cover during the rainy seasons, and the nourishment of the animals, and then decline during the dry period. This cyclic regime had been terminated about 22,000 years ago, during where soils and crops improved considerably in the northern area of the African Great Sahara, and resulted in prolific farms for the profits, welfare, and civilization of the human being. As you see, my dear students, the termination of the glacial period gave the chance for having these white farms and the civilization of the human being. Also, we have now a balance of the Earth's crust and its relation to some others. We look to these changes in the Earth's crust itself. Sometimes we have high lands and others we have low lands. And we need to know exactly the relation and the equilibrium and the balance between these two levels, high and low levels of the land. Man carries out his daily activity on the surface of the earth, where he builds up his living complexes, factories, and perform his agricultural and social environment. To fulfill this daily requirement, he seeks for particular areas where he finds his needs of rocks, building materials, and cultivatable plains. These areas are originated from different physical and chemical processes, such as running water, rivers, rains, and flash floods, wind, marine action as waves, current, tide, and glacial erosions. All of these acting on the earth and give different topography. All the agents participate in breaking up the rocks of the crust surface and transporting and settling down, forming floodplains. Terrains of gentle slope of flat areas where man constructed his industrial districts, productive farms, and living settlements. It is estimated that the rate of removal of materials by these erosive agents from mountainous regions and continents to be leveled nearly about 21 million years. So if we think these agents are continuing work and fracturing of rocks, it takes 21 million years to make the earth leveled, almost in the same level. Since the globe is more than 4 billion years old, it is logic that the earth's surface would have been enabled many times unless there are forces tending to oppose this leveling and this mechanism to overcome the external destruction processes. The settling of sediments on the ocean floor, deposition of rivers load at their estuary, building up deltas, all of these sediments are accumulated in sand grains forms in the form of dunes and desert areas act as balancing force for the crust, balancing factor in the Earth's crust. This meantime we have folding and faulting created in the mountainous terrains, and subsidence rates on parts of the most of the land masses under ocean water. In both cases, the configuration of the Earth changes radically. Nevertheless, the globe equilibrium is maintained and compensated for the loss by new deposits. So the deposits taken from the highland, it is laid down in the lowlands. It is confirmed that the idea of isostatic equilibrium plays an important role in the crustal balance. It results in the formation of mountain chain with their light rock constituents of average density 2.7 grams per cubic centimeters compared to the heavy rocks below and the mantle of an average density of 3.3 grams per cubic centimeters. By this, my dear students, we come to the end of our today's program. Until we meet next time, have my best wishes and goodbye.